Okay, let's get started. So in this lecture, second lecture in this module, that is reasoning under uncertainty, we have already covered the prerequisites, but now in the previous lecture, we talked about Bayesian networks. And from there on, we are now continuing to Markov chains. So in order to understand hidden Markov model, we need to first understand what is Markov chains. Okay, then only we can understand that topic perfectly. So in this lecture, I'm only going to discuss Markov chains, but this is very, very important. And we are going to discuss that in a lot of detail. Okay, so let's get started. Okay. So let me give you a simple example. I hope everyone have covered the Bayesian networks lecture. So I'm simply making one network here. Let's say suppose this is the network given to you, right? Now, if I ask you to write the full joint distribution here, probability of A, B, and C. So what I can write here, I know that A is not conditionally dependent on anyone. So we can write probability of A multiply. What about B? B is conditionally dependent on A. So we can write like this. And what about C? Actually, we can write this as well. Probability of C given B and A. But I told you in the Bayesian network lecture, instead of writing this, so in Bayesian network, we talked about, right, when we talked about like this thing can be written simply as probability of C given B. Because this is the assumption. So basically, this is the assumption that we have. And this assumption we are going to say in this Markov chain. Basically, this is the Markov property. What this property says that the next state that you are talking about, the probability of that state will depend on the current state. The probability of that state will depend on the current state, not the states which are previous to the current states. Okay, this is the property, Markov property, and which we use in Bayesian network also, right? So instead of writing this probability of C given B and A, we can simply write probability of C given B. Are you getting this point? Again, I'm repeating what it means. It means that probability of C only depends on B, not on A. And what Markov property says, it says that the probability of this next state, let's say you are present here, you are standing here, this is your current state. Okay, and this is your next state that you are talking about. So probability of the next state will only depend on the current state, not on the previous state. Is this clear? So this is Markov property in short. Okay, we will see the complete detail about this, but this is the brief idea that you can understand. I hope it is clear. This is clear to all of you. So let's talk about it. Let's read it a few things. So the HMM, what is HMM? HMM is Hidden Markov Model that we are going to cover in the upcoming lectures. Okay. So Hidden Markov Model is based on augmenting the Markov chain. What is Markov chain? Markov chain is a model that tells us something about the probabilities of sequence of random variables. You can consider this example. I told you that the states are nothing but the nodes are nothing but the random variables or stochastic variables, you can say. So it tells us about the probabilities of sequence of random variables, which we also call it as states, each of which can take on values from some set. Okay. And what it says, a Markov, you can see here, a Markov chain makes a very strong assumption that if we want to predict the future in the sequence, all that matters is the current state. So this point is very, very important. Are you getting this? So if you want to predict the future, all it matters is the current state. The states before the current state have no impact on the future except via current state, right? Or you can consider the example of also like it is as if to predict tomorrow's weather, you could examine today's weather, but you were not allowed to look at yesterday's weather. I hope this is crystal clear to you. What is this Markov chain and the strong assumption, the very strong assumption, the property that we are considering for Markov chain. Okay. So this is the example that we are continuing here. So as you can see, these are the states that we have: hot, cold, and warm, right? And you can see here. So all these are the states. So whenever we talk about Markov chain, yes, sequential data. We talk about sequential data, Chandana. Okay. For example, let me give you one more example. Okay, just wait. Let me give you one more example. Let's say you are present at some location, maybe Mumbai. Okay. And let's say from Mumbai, you are maybe going to Delhi. You can go to Delhi, let's say. And let's say you are going to Gujarat. Yeah, you can say the time series data also. But it has to be sequential. So carefully see this. Yeah, yesterday's data cannot be used. So just carefully see this example also. You will get more idea about it. So let's say before Mumbai, let's say maybe you are coming from Pune. Okay. So from Pune, you go to Mumbai. And then from Delhi, maybe you are going to, let's say, Uttarakhand. Okay. And then from Gujarat, maybe you are going to Rajasthan. And then let's say from Uttarakhand, you are going to Rajasthan. Okay. Now, what is the probability? Let's say you are present over here. You are present that you visit. Now you are present in Mumbai. What is the probability that you go to Delhi next? Okay, that you go to Delhi. What is the probability of that? So probability of going to Delhi, that only depends on Mumbai. It does not depend on Pune. I hope now with this example also it is crystal clear to you. So yesterday's data is of no relevance. You are not going to use it. Okay. I hope it is clear. Fine. So the same thing is mentioned over here. So these are some examples as you can see here. So, but to understand these examples, I will be taking a very basic example, or let's consider this one also, or let's consider this one, then we will be seeing more examples. So what it says, this is a Markov chain. You can say this is a Markov chain. So in Markov chains, there are certain components that we have. One is the set of states. So here, if you see this first diagram, if you consider, we have three states here. One is hot, cold, and warm. So these are the three states that we have, right? Now, if you are, let's say, present at hot, if you are, let's say, present at this particular state, now the probability of going to the next state, which is cold, if you are present at, let's say, probability of going to cold state, given that you are present at hot state, what is the probability? That is 0.1. Okay, so these edges, basically this has to be a directed graph. This has to be a directed graph. And what else? The second thing is these edges, you have what? Here you have the probabilities. What is the probability that you are present at the current state and you are going to the next state? Similarly here, if you consider this hot state also, what is the probability that you are present? The next state is also going to be a hot state. So there is a self loop for that, and the probability is 0.6. This is Markov chain. Okay. What next? The important thing that we have to consider here in the Markov chain, if you carefully observe this first diagram or any Markov chain diagram, whatever outgoing arrows you have from a certain state, the sum of those probabilities will be 1. So let's find it out here. Let's verify it here. So this is the outgoing arrow from hot state. This is the outgoing arrow. This one is also outgoing arrow. If you add all these probabilities, you will find that the sum is equal to 1. So 0.6 plus 0.3 plus 0.1, that is equal to 1. Similarly, you can verify from this cold state as well. 0.8 is there, 0.1 is there, 0.1 is there. So that also sums to 1. This is the next thing that we have to consider. Is this clear so far? Do you have any doubt? Okay, fine. So what it says, the Markov chain on weather, this one we are talking about, this one is weather, related to weather, showing states and transitions. So these are the transitions, and these transitions, basically these transitions are nothing but the probability from one state to another state. Now these transitions you can mention in the form of adjacency matrix. How many of you know what is adjacency matrix? Even if you don't know, that does not matter, just let me know this. Okay, one student. Okay, let's say this with a simple example. Let's say you have, let's say, a state A, a state B, and let's say you have a state. Okay, let's consider simple example. So let's say this is the Markov chain. So probability is maybe point. Okay, let's consider one more. So 0.3. Let's say here it is maybe 0.6, 0.4. Okay, and let's say from C, maybe this is 0.5, and let's say to A it is 0.5. Okay, now these transition probabilities you can also mention in the form of adjacency matrix. So what do we mean by adjacency matrix? So we are going to have like A, B, C, and this is how we are going to have this. So it is a kind of matrix. Kind of matrix means, I mean, it is a matrix, right? Okay, not kind of matrix. So what we see, like if I ask you a simple thing, what is the probability that you are present on a state A and you are going to state A only? So you will find that there is no self loop. There is no self loop on A, right? So can I say the probability of that is 0? Understood? Okay. What is the probability that you are present on a current state A and you are going to state B? So can I say it is 0.7? Just see this one. So this is how you fill the probabilities here. Now I hope you can fill the rest of as well. So probability that you are going to see, now you are present on A, so that is 0.3. So this is how you can fill that. Okay, so let's quickly do it. So this is 0, and B to A is 0.6, B to C is 0.4, C to C is 0.5, C to A is 0.5, C to B is 0. So this is nothing but the transition probability matrix. This is the transition probability matrix. Is this clear with this example? Okay, so it is talking about the same thing. So transitions are given here. So here they don't have they haven't mentioned that in the form of matrix, but yes, basically they are talking about the transition probabilities that we have on the edges. And a start distribution pi is required. Now what is this pi? This pi indicates when I'm writing like this, let's say pi of 0. So this is a vector, and this pi indicates that what is the probability that you are starting from a given state, or you can say, in other words, you can say what is the initial probability distribution. What is the initial probability distribution which represents, like for example, if I say let's say the probability of starting from a given state. Let's say if I start from C, randomly I'm saying, let's say if I start from C, so what will be the initial distribution? It is going to be 0, 0, 1. The sum of this will always be 1. The sum of this will always be 1. The sum of this will always be 1. The sum will always be 1, if you carefully observe here. Because I told you one thing, right? That from every state, whatever outgoing arrows is there. Just wait. I'm coming to pi again. So I told you that whatever from any given state, the outgoing arrows, if you add all the probabilities of outgoing arrows, it will always be 1. So that is the reason why every row, if you add every row, the probabilities of every row, it will be equal to 1. This is one thing. Second thing is pi is the initial state. It represents, as you can see here, this is a starting distribution, right? From where, what is the probability of starting from a given state? So it may be like this, or in this example that they have given, it is like this, that what is the probability that you are state? What is the probability that you are starting from a cold state? What is the probability that you are starting from a warm state? So these are the probabilities given. And if you add all these, it will be also 1. And it is also mentioned here, A would mean a probability of 0.7 starting in the state 2, that is cold. Is this clear? So this is the starting distribution, or you can say initial distribution, that is pi. This is a row vector that you have. Now, if you have any doubt, please ask. So far, so as of now, we are just talking about the terminologies, okay? So first of all, terminologies has to be clear, then only we can proceed. Take your time, let's say 15 seconds. And if you have any doubt, please ask. In anything that we have discussed so far. Clear? Shall we proceed now? Okay. So now we can proceed. Now, what is the assumption, the Markov's strong assumption that he had made? What is that? That is simply, you can see here, this is the Markov assumption, and it simply says the probability of the next state, given that, as you can see here, all the states, it is given that all the states, all the previous states is given. So instead of considering all the previous states, you are just going to consider the current state. So if you are present at I-1 state and this I is your next state, so that all it matters. So basically this is the current state, it all matters. Before that, that means the previous states, it does not matter at all. This is the Markov assumption. Is it clear? So you can just give it a read. All these things I've already explained and you will be understanding. Okay. So let's proceed. So now let's see, as I told you, the components. So what do we have in Markov chain? What are the components that we have? One is a set of n states. So there can be n states, let's say from Q1 to Qn. These are the set of states. And what else is there? So we have something called as transition probability matrix. So just now given the example, right? How we write the transition probability matrix. So as you can see here, from A11, from A12, and then AN1, then up to ANN. So that is the matrix that you have, okay? And what else it is mentioned over here, that the sum will be, so it is mentioned here that each Aij represents the probability of moving from state I to state J. So like in this example we have considered, so probability of moving from A to B, that is 0.7, clear? And it is such that summation of Aij, where j is equal to 1 to n, will be equal to 1 for all I. That means the sum of the row, every row will be equal to 1. I hope it is clear. Fine. So this is the second component. What is the third component that we have? That is your initial probability distribution, which we talked about just now, that is pi. So pi is the initial probability distribution over states. So pi I is the probability that Markov chain will start in state I. Okay. So it will represent. So pi I, that means particular value that you have in a particular in that pi vector, that row vector. Okay. So pi I, so from state I, what is the probability that you are going to start from the state I? That will represent the value at that particular vector. Some states j may have pi j is equal to 0. So it is also mentioned that some states can have probability as 0, as I told you here. So this kind of, you can say initial probability distribution is also possible, where that you are going to start from, you have to start from C. So as the probability is 0 for A and B, that means you cannot start from B. So initial state will always be from C only. Clear? And also it is mentioned, this thing also I told you, that sum of you can say summation of I is equal to 1 to n of this pi vector will be equal to 1. That means if you sum all the values of pi vector, that will be equal to 1. Is it clear? The same thing is mentioned over here, state space. I'm not repeating again. So just from the various sources I have mentioned here, initial distribution, that is pi 0. Pi 0 means the initial distribution, the starting distribution that we have. And that, if you add all the values, that will be equal to 1. The same thing is mentioned over here. And here it is talking about the probability transition rule, which is nothing but it is talking about the transition probability matrix, okay, which is a n by n matrix whose entries are all non-negative and whose row sums to 1. And this is what is, we can say this is our Markov assumption, the probability of next state given that probability of current state. So I hope so far whatever we have discussed, is it all clear to you? Do you have any doubt? Anyone? Manjunath, Sumit, Abhas, Chandana, Hema, crystal clear? Okay. Fine. Now let's proceed to the next topic. That is the subtopic, we can say, the basic limit theorem of Markov chains. Now this is very interesting thing. So carefully understand this. So what this limit theorem says, so let's consider through one example. That will be easy way to understand. So this is a figure given to you, and you can say there is a Markov chain given to you basically, right? So this is the example of a random walk on a clock. So when I say a random walk on a clock, that means either you can stay at the same state, or you can go to the you can go in the anti-clockwise direction, or you can go to a clockwise direction. So from any given state, if you carefully observe this diagram, if you are present at any particular state, let's say you are present at 2, right? So from state 2, either you can go to the same state, or you can go to the in an anti-clockwise direction, that means you go to 1, or you can go to 3. And the probabilities of going in any direction, that is 1 by 3. In this example, it is given that it is 1 by 3. It's not like it has to be same. No, it's not like that. Just for this example, it is given that the probability of moving from one state to another state, that is 1 by 3. Clear? And total there are 6 states present over here. Now what this example says, so as it is mentioned that total 6 numbers are there from 0 to 5, right? And carefully see this, we perform a random walk by moving clockwise, moving counterclockwise, and staying in place. That means if you stay at the same place, the probabilities are 1 by 3 each at every time in. So can we write like this also, this distribution, that P of I comma j, that means if you move at j, the probability is 1 by 3, where j can be I minus 1 mod 6. If you are moving to the anti-clockwise direction, then this is applicable. If you are moving to the clockwise direction, then this is applicable, right? And if you are staying at the same state when j is equal to I, then also the probability is 1 by 3. So can I say that transition matrix can also be written as this, in this way, as this distribution? Yes or no? Okay, good. So now what else it is saying? Let's say, suppose we start at x0 is equal to 2. So it is simply saying, let's start from state 2. Now, if you start from state 2, let's say this is the vector, the initial distribution, the pi is given to you. So pi 0 means the initial distribution, pi 0. That means the initial state, you can say, from where you can start. So this is given to you. This is the initial distribution, probability distribution given to you, 0, 0, 1, 0, 0. So as it is saying that you are starting from 2, so let's say this is the pi vector. Now what you will observe, how we are calculating this pi 1. So carefully understand this. You have noting, let me denote it by A. So this transition matrix, I'm not going to draw the entire transition matrix because 6 states are there. So 6 values will be here, 6 values will be here. Just understand this thing, that this is your transition probability matrix. Now you have a pi, let's say pi 0, you have 0 0 1 0 0. This is what you have, right? 0 0 1 0 0 triple 0, right? Triple 0. 6 values are there, right? So now what we do, we basically multiply this pi with a. So this is a row vector, yes or no? I hope everyone has covered the linear algebra part. So now we are using the linear algebra concepts here. And this is a matrix that you have, and this is n by n matrix. So in this example, you can say this is a 6 by 6 matrix, and this is what? This is your 1 by 6, right? 1 row and 6 columns are there. So this is the shape. Now, once you multiply, let's say pi 0, you are multiplying with matrix multiplication, you are performing with a. So you are going to get some result, correct? So now once you multiply this, this is what you are getting. Let's say pi 1, this is what you are getting. And you can verify also. You can verify also. How you can verify? This is very simple. Let's say you are starting with this from state 2. Now from state 2, either you can move to the same state, or you can go to this state 1, or you can move to this state 3. So can I say that if you multiply this, so these three values will be 1 into 1 by 3, 1 into 1 by 3, 1 into 1 by 3, rest all will be 0. Can I say this? Yes or no? So I can write here for your reference that pi 1 is nothing but, or you can write like this, pi 0 into maybe in this scenario you can say p is equal to pi 1. Is this clear so far? This is what we have done. Understood? Okay. Now it is easy to calculate. So what we have done now, so we have calculated this pi 1. Now we have used this pi 1 and we have performed this matrix multiplication again with the p, and now let's say we are getting pi 2. So these are the values that we are getting. So we are not performing calculation because it will be time consuming, but we know that we can do this. Okay. So this is what we are getting. Then further you can say pi 2 matrix multiplication, and you are getting this pi 3. Now what is going to happen? So this is, let's say after one step, then after one step what you are getting, then maybe after one step what you are getting. So after 3 steps, this is the pi vector that you have, right? Now if like this, if let's say the number of steps that you are taking is very huge, and maybe you can say it is tends to infinity. If it tends to infinity, in that case, this pi vector that you are getting, that will stabilize. This pi vector will stabilize, or you can say it will approach the uniform distribution. What does that mean? That means that this pi of a, in our example, will become pi only. Now I'm going to ask you a simple thing. Have you seen this kind of thing anywhere else before? This kind of equation? Think about it. Exactly. Very good. So this is, can I say this is same as writing this? This is similar to this one only. So can I also say that this pi is nothing but the eigenvector here? Yes or no? Right? And here we are considering, we can consider that lambda eigenvalue is equal to 1. For our example, for our case, we can say that here always the eigenvalue will be equal to 1, right? Or you can just rearrange this and you can write like this also. So these two equations are same now, right? So this is what we are saying, that once you get this thing, after thousands of steps, or maybe after, let's say, n tends to infinity. So if you simulate this, you will be getting this thing that even if you are multiplying again and again with the pi, still you are going to get it. So that will stabilize. So once it stabilizes, we call it as a stationary distribution. And this is what the theorem says, this particular theorem, that is basic limit theorem. Again, I'm telling you, these theorems are not important for you, but it is important in the context of understanding the Markov chain. Okay, so it's not like everything that I'm covering is very important, but yes, it will give you in-depth clarity of what we are studying and why we are studying. Okay, I hope you understand this. So this basic limit theorem, it says that let x0 x1 be an irreducible aperiodic Markov chain. Now you may be asking, sir, what is irreducible? I will be discussing that. Aperiodic I will be discussing in the upcoming lectures. So what is be irreducible Markov chain. Just understand that this Markov chain we are talking about having a stationary distribution. Now this is having a stationary distribution, and when we get the stationary distribution, so let x0 have the distribution pi 0 and arbitrary initial distribution. Pi 0 is initial distribution. Then n tends to infinity. That means after these many steps, you can say, or close to infinity, after many steps, pi n of I will be equal to pi of I only. So in other words, you can simply write like this, that whatever is your transition matrix, that will become, this thing will become pi only for all states I. So as you can see, this has stabilized. Now again, I'm saying that it's not like this will be always same, like all these values here in this example, it may be same, but in other examples, this pi, whatever is the value of the pi, that can be different also, right? Okay, that maybe here I'm having 0.35, here maybe I'm having 0.25, 0.79, something like this. So that shows the probability. That means after 1,000 steps, after a huge number of steps, what is the probability that I will be on this particular state? Are you getting this? Now I'm relating this concept with why we are calculating it. So it's like this. You can understand from this example. Yeah, let's say I start from maybe, let's say our given example, let's say I start from state 2. Now what is the probability that I will be, after taking, let's say, 1 lakh steps or a huge number of steps, I will be present at state 4? Now it seems very difficult to calculate, right? Like after so many steps, how, like where we should be, right? Or what will be the probability of reaching at state 4? So this pi is indicating that. So that probability distribution that you are going to get after so many steps will be explained by this one. So these are the probabilities that you are going to get. So after taking n number of steps, this is the probability that you will be reaching this particular state. Is this clear to all of you so far? Do you have any doubt? Okay, great. So they have also talked about stationary distribution that I told you just now. So again, the same thing is mentioned over here. I would suggest you to just give it a read. Just at least give it a read after the class. Okay, not now, after the class. Okay, the same thing is mentioned over here, nothing different. Fine. Now let's consider this example, another example, to understand the upcoming concepts. So there are 3 states present over here: state 1, state 2, and state 3. And let's say a frog is present at state 3. Okay. And again, you can understand this Markov chain easily. You will be saying, sir, yes, okay, if I'm present at state 3, the 1 by 3 is the probability that I will be going to the next state, which is 1, right? Similarly, you can just see that from any given state, the outgoing arrows probabilities will sum up to 1. So all these things you know already now, right? So let's see what it is saying. So this is a Markov frog. So what it says, let's do an example. Suppose the state space is 1, 2, 3. So there are 3 states. Initial distribution is pi 0. So now carefully see this. This is the initial distribution given to you. That means the 0.5, or you can say 1 by 2 is the probability that you will start from state 1. 1 by 4 is the probability that you will start from state 2. And 1 by 4 is the probability that you start from state 3. This is the initial distribution that is given, or we can assume. Now, what is the probability matrix, transition matrix? I told you that from this given Markov chain, you can build the transition probability matrix. Okay, so this is what it is, right? Now, so what it says, again the same thing, that let's say this frog, to start with, he chooses his initial position x0 according to the specified initial distribution pi 0. Okay, so this is the pi 0 that is given to you, and he chooses the initial position x0. Now what can be the x0? It may be possible that x0 can be 1, the state 1, state 2, or state 3. So for that purpose, what he does, that he's using his computer to generate a random number, right? He generates a random number between 0 and 1. So uniform distribution from between 0 and 1, he generates a random number. So once he generates the random number, let's say that this u0, that comes out to be 0.8419. Now carefully understand this distribution. It is very simple, nothing fancy here. Carefully see this. State 1 means what? You know the probability of starting from state 1 is 1 by 2, right? So can I say from 0 to 1 by 2, this is going to be the uniform distribution of state 1? Do you agree? Yes or no? Yes. For state 2, can I say if starting probability is 1 by 4? So I can say from 1 by 2 to 3 by 4, you can allocate to this one. And for the third one, you can say from 3 by 4 to 1. Because if you say 1 minus 3 by 4, that is also 1 by 4. 3 by 4 minus 1 by 2, that is also 1 by 4. So I hope you understand that we have just distributed the uniform distribution for these three given states based on their probability. Clear? So let's say initially it generates this random number generated by his computer is this one. So if this is the random number generated, so can I say that, okay, we can start from state 3, right? Because this number lies between 3 by 4 to 1. So let's say it starts from state 3. Now then the frog chooses x1 according to the probability distribution in row 3 of P, right? So just a minute. Okay, fine. So let's say it starts from this state 3. I hope this diagram is visible to all of you. So this frog starts from state 3. Now there are three possibilities. Either one possibility is it can go to the same state, so the probability is 1 by 3. It can go to the state 1, that is also 1 by 3. It can go to state 2, that is also 1 by 3. So this is what it is mentioned over here, that the probability distribution will be 1 by 3, 1 by 3, 1 by 3, right? Now, so you can say, can I say that this is pi 1? You can say, right? Because this is the next probability distribution that we have calculated, right? Now, again, to predict this, again, further the states can be divided again. Based on this probability distribution, we can divide like this: 0 to 1 by 3, 1 by 3 to 2 by 3, 2 by 3 to 1. Just consider this example just to understand the concept. Okay, it is not important for you, like for your gate exam point of view. Okay, I hope you're getting this. Fine. Now, the number that is generated is U1, which is 0.1234. So now if this lies between, you can say 0 to 1 by 3. So the next state will be x1. So from, you can say from third state, it will go to the first state, and so on and so forth. You can say the same thing you can apply, and n number of times, and this will continue like this. Okay, this will continue like this. So we can say clearly in the previous example, the Markov property. So now carefully see this, the application of Markov property. So let's say we came up with x0 is equal to 3, x1 is equal to 1, x2 is equal to 2. This is the sequence that we followed, right? In the previous example, we started from state 3, then we went to state 1, and then we went to state 2, right? From state 1. So then the conditional probability distribution for x3, we can write like this, right? That what is the probability of x3 is equal to j, right? x3 is equal to j, that means the next state, given that x0 is equal to 3, x1 is equal to 1, x2 is equal to 2. Now we know what is Markov property. Markov property says that the probability of next state. So let me just explain you here also. From x3, you went to x1, you went to x2. Now, what will be the next state? Right? What will be the next state? So let's say if I say maybe it is m. So can I say the probability of next state m, next state would be m, given that I can write x2 also, x1 also, x3 also. But what this Markov property says, it says that these two are irrelevant now. We are just going to consider x2. Do you understand it or not? Is this clear or not? So the same thing is mentioned over here. We can write like this, but ultimately we can say, using the Markov property, we can say that this will be equal to this only. X2 is equal to 2, which is the current state. Given current state, what will be the next state? Clear? Any doubt, anyone? And this makes a lot of things very easy for you, right? The computation will be very easy for you. And in formal way, you can see this is the proper definition. So what is more important for you? You should know, you must know what is Markov property. This is the first thing. You should know what are the components in the Markov chain. This is the second thing that you should remember, or you should understand clearly from whatever we have discussed so far. Clear? Okay. Now let's proceed. Now, what is recurrence, irreducibility, or classes? So let's understand these through examples. Let's say this is the Markov chain given to you. Now, let's say if you start from state 0. So from state 0, either you can go to state 0 itself, or you can go to state 1. Correct? Now, let's say once you reach to state 1, is it possible that you can come back to state 0? No, right? There is no way going back to state 0. So if there is no way going back to state 0, we call this state, this 0 state, as a transient state. We call it as a transient state. Is this clear? So what is transient state? In formal way, we can say that the probability of reaching back to 0 state is less than 1. Let's say if I start from 0, there is one possible way that I can reach to 0 through this way, right? I can go back to 0. But if I go back to if I follow this path, if I follow this random walk, in that case I cannot go back to this. So if this is the scenario, that means it is not bound to happen that I will reach to 0 state after some steps. Are you getting this? Clear? So I call this 0 state as transient state. A state is called as transient state when the probability of going back to that state is less than 1. Understood? Okay. So we can say when the probability of going back to that particular state, let's say if I say 0th state, is less than 1. That state we call it as transient state. Okay. But now carefully see this. Let's say I'm talking about state 1 now. Okay. So from state 1, let's say I'm present at state 1. Can I bound to happen that you will reach state 1? Can I take this path, go to state 2, and then come to state? Is there any lag from my side? Am I properly audible? Fine now? Okay, lag is there. Okay, let's just wait for a few seconds to stabilize. Yes, everyone. Still there is a lag. I was saying is, you understood this, right? Why we are calling 0 as transient? Everyone from there. This is clear, right? Okay. So then after that, what I was saying is, let's say if you start from state 1, some steps, definitely this is bound to happen that you will be reaching the state 1 for sure. So let's say you take this path. Let's say you take this random walk. Again, you are coming back to 1. Let's say you follow this random walk, you go to 2, and then from 2 you come back to 1, right? So can I say the probability of coming back to state 1 is 1? Can I say this? So probability of coming back to state 1 is 1 here. Correct? Can I say the same thing for state 2? Can I say the same thing for state 2? Let's say if I'm starting from state 2, you will go to state 1. Maybe you can take this random. So can I say the probability of coming back to state 2 is also 1? Yes or no? Is this clear? So when it is bound to happen, or in other words, you can say the probability of coming back to the same state is equal to 1, we call those states as reducible, recurrent state. So in this diagram, I can say that 0 is my transient state and 1 and 2 are my recurrent states. Is this concept clear to all of you? Any doubt? Just let me know if it is clear or not. Okay. Now this thing is clear. So the next thing is, if in the Markov chain, so this is a Markov chain given to you. If in the Markov chain, if all the states, if every state is not a recurrent state, or in other words, you can say if there exists at least one transient state, you call that particular Markov chain as, I'm sorry, you call that particular Markov chain as reducible Markov chain. Is this clear? You call that particular chain as reducible Markov chain. That means there exists at least one transient state. Then we can call it as reducible Markov state. Okay. And if I have this type of Markov chain, now just answer this. Do we have any transient state here? Everyone, try to answer this. Do we have any transient state in this Markov chain? If you say, if you start from any state, let's say you are starting from 0, it is bound to happen that after certain steps, after certain number of steps, you will reach back to 0 also. Yes or no? Let's say you can take this path, fine. You go to 1, you take this path, you go to 2, and then after some steps, you will come back to 0. So can I say now 0 is my recurrent state? And 1 is already a recurrent state, 2 is also a recurrent state. Can I say all the states present in this Markov chain is a recurrent state? Yes or no? So now, if all the states present in your Markov chain is a recurrent state, we call it as irreducible. We call it as irreducible Markov chain. Now, there can be one question that can arise from this concept. Sir, we understood what is transient state, what is recurrent state, but why we are calling it as reducible Markov chain? So as the name suggests that you can reduce it further. What do I mean by that? That means if whatever is your transient state, just take it out from the Markov chain. If you just simply take it out from the Markov chain, can I say now this particular state will be your, you can say irreducible, or you can say simply this particular state is recurrent state? Yes or no? Whichever state is your transient state, you just you can say separate it out from the Markov chain, already existing Markov chain. Now this state will become recurrent state, because if you start from 0, again you will reach back to 0. The probability is 1 in that case. Reaching back to 0, the probability is 1, right? So can I say now this is now this particular state has become another Markov chain, because only one state is present in this, and that is recurrent. So this is now irreducible. This will become irreducible Markov chain, that you cannot further reduce it. And this is already a irreducible Markov chain. Yes or no? Is this point clear? That is the reason why we are calling it as a reducible Markov chain. So whenever there is a transient state present, we can split it out, or we can separate it out, and we can make more Markov chains, and that will become, eventually that will become irreducible Markov chain, as you can see in this example. Now this is a separate Markov chain, and this is another Markov chain. Is this point clear? Okay, fine, good. And both are now irreducible. Both are irreducible now. Now let's see this one. So this is another Markov chain, and this is very famous Markov chain, that is gambler driven. But we don't have to go to don't have to go by that name, but just carefully observe this Markov chain. So what do we have here? So if I talk about, again, can I say 0 from 0? You can go back to 0, that is fine. But from 0, you cannot go to 1, right? From 0, you cannot go to any other state, correct? And the same thing is happening for 3 also. State 3 also, you can go to 3, but you cannot go to any other state. So in these scenarios, what we do, we divide these into classes. We divide these into classes. So we make, you can say, we make this as a separate class. We make this as a separate class, and these two classes are communicating with each other, right? These two states, these two states are communicating with each other. So we are going to keep them in a single class. Okay. So whichever classes that communicates with each other, we call them as communicating states, and communicating states, we keep them in a single class. Like in this example, if you can see, 1 can communicate with the 2, 1 can communicate with the 2, and 2 can communicate with 1, right? So that is the reason why we are keeping them in a single class. Okay. And 0 can communicate with itself only. It cannot communicate with any other state. So we are keeping it in a separate class. And same case goes for state 3 as well. So what we have done here, we have divided them into classes. We have divided them into classes. So this concept of reducible, recurrent, transient, and classes, is it clear to all of you? Any doubt in this? Okay. This is just a classification that they have done, nothing else. Okay. And the same thing is mentioned over here also, classification of states. So as you can see here, 2 states I and j that are accessible to each other are said to called as communicating classes. And we write them as like this, that I can communicate with j, j can communicate with I. Or in other words, you can say from I you can go to j, from j you can go to I, right? And these are the properties, 3 properties that we have for the communicating classes. You can just give it a read, you will be able to understand. Simple statements are mentioned over here. The meaning I have already explained it to you. Is it clear? Any doubt, anyone? This thing I hope this is also clear to you. What is the meaning of this particular definition? So it states that any state communicating with itself. So P of I, that means previous state, what is the probability of reaching to the same state itself, given that you are present on the same state, that is equal to 1. This is this is what it says. Clear? Okay. So far, whatever we have discussed, is it clear to all of you? Now we are going to proceed to the next topic, that is n-step transition matrix. The important topic, I can say. Is this clear? Shall we proceed now? So whatever we have covered so far, are you finding it easy to understand or not? Just let me know this. Go. Read it from a standard textbook or some standard articles or university PDFs. You will not find it very easy to digest. So, but still, I'm trying to make you understand. I hope you are finding it very easy, these concepts. Okay, so let's talk about the matrix. Any doubt? Diagram of class is what? When we can reach 0 again, right? Yeah, from there is a self loop, right? There is a self loop. There is a self loop, so you can go to the same state. That means 0 can communicate itself. That is fine, but it cannot communicate with any other state like 1, 2, 3. So that is the reason why we are keeping it in a separate class. Similarly, for state 3, we are keeping it in a separate class because 3 cannot communicate with any other state. Is it? Shall we proceed now? Thank you. Fine. So n steps transition matrix. Let's understand what is the concept here. This is very interesting concept. You will also find it interesting for sure. Carefully see this. So this is a Markov chain given to you. There are 3 states, 0, 1, 2, and the transitions are also mentioned. The probabilities are mentioned in this transition probability matrix. Okay. So this is a matrix A, and these transitions probabilities are mentioned in this matrix. Fine. Now what we are trying to find out, what is the problem statement? The problem statement is very simple. What is the probability of reaching state J from now? Let's say state J, I'm present at state I want to reach at state J. What is the probability of reaching to state J from state I after taking exactly n steps? Don't you think that this problem statement is very hard to compute? That after n steps, what will happen? Like, what will be the probability? It seems hard, right? It seems hard. So what I'm going to do, we are going to simplify it. We are going to take the base step. So carefully understand this. So basically, this is what we want to find, right? From state I to state J in exactly n steps. So let's take the basic step. Let's substitute the values. So now what we want to of reaching to state 2 from state 0 in exactly one step, after exactly one step. So I can represent like this: P of probability of from reaching state 2 from state 0 exactly one step. So carefully see this: from 0 to 2, right? Can I say this is the only path? I mean, this is the only way, like in just one step, if you have to reach, this is the only way. You will say yes. So what will be the answer? Can you tell me what will be the answer? What will be the probability of this? Anyone? Think about it. 0.3, right? Exactly. Can I say this is going to be 0.3 from 0 to 2, right? So this represents like this. I can write like this also for your reference. This is 0, this is 1, this is 2. This is 0, this is 1, this is 2. This is the adjacency matrix, right? Nothing else. So from 0 to 2, can I say this is the probability in just one step if you have to reach? So your answer will be 0.3. Your answer will be 0.3. As simple as that. Let's make it more complicated. So you can simply say that it is nothing but, so can I say that P of ij after exactly one step, probability of moving from state I to state j after exactly one step, can I say this is equal to A of ij? This is just now, this is we have seen, this is what we have seen, right? Yes. Now carefully see this. What is the probability of reaching state 2 from state 0? The same thing, but after exactly 2 steps now. So this is what I want to find out. P of 0 to of 2. That means from state 0 to state 2 after exactly 2 steps. So let's try to do the random walk. Okay. So can I say one way of reaching from state 0 to state 2 in exactly 2 steps will be this one? Carefully see this, everyone. 1 and 2. Correct? 1 and 2. What else? 1 and 2. Again, we can reach like this. Is there any other way? Yes. Carefully see this. 1 and 2. Is this clear to all of you? So can I say this, that this is same as writing, you can say, so I'm directly writing the values. So this is same as 0 to 0, that means 0.5. Can I say multiply by 0 to 2, that is 0.3, plus then 0 to 1, so 0 to 1, that is 0.2, and then 1 to 2, so 1 to 2, that is 0.2, plus I can say 0 to 2, that is 0.3, multiply 2 to 2, 2 to 2, that is 0.8. Is this clear? Do you have any doubt here so far? So again, we can just verify the values here. From 0 to 0, that is 0.5, fine. Then from 0 to 2, so 0 to 2, that is 0.3, so this is correct. Then from 0 to 1, so 0 to 1, that is 0.2, fine. Then 1 to 2, so 0, 1, 1 to 2, so that is 0.2, that is also correct. Then 0 to 2, so 0 to 2, that is 0.3, and then 2 to 2, so 2 to 2, that is point, okay, this should be 0.1. This should be 0.1, right, everyone? This should be 0.1. Yes. So what do you get? This is your 0.15. This is your 0.04. This is your 0.03. So that will come out as 0.22, right? Is this clear? Yes, Abhas. Why 2 to 2? Yeah, that is basically we are talking about exactly after 2 steps. Oh, exactly after 2 steps. That means from 0 to 2, and then again 2 to 2. That means because the problem statement is like this. After exactly 2 steps, I should reach to state 2. So after these 2 steps, can I say still I'm present at state 2? Yes or no? Exactly. This is what it is mentioned, right? Exactly 2 steps. Exactly 2 steps. Is this clear so far? So finding is not very important for us, but what we are going to learn from this, that is important. So this thing, I hope this is clear to all of you, right? Simple stuff. Okay, but how we can generalize this? So can I say it is equivalent? So whatever I have written the numerical values, can I say this is same as this thing? Just carefully observe. From A to 0 to 1, 0 to 1, and then 1 to 2. So this part is done. 0 to 0, 0 to 2. So this part is done. And then 0 to 2 and 2 to 2. So this part is done. Yes or no? Correct. If let's rearrange this. So this part I can write here, then this part, and then this part. So can I say this is what we are going to get? Just I have rearranged this. This was present here, so I have now written here, then this, then this. Now can you see some pattern over here? Do you find any pattern over here? So if you carefully observe, you will find a pattern here. And what is that pattern? That pattern is this a of 0, 0, a of 0, 1, a of 0, 2. This is that value. And what else? This a of 0, 2, this a of 1, 2, this a of 2, 2. This is that value. So don't you think this is a kind of matrix multiplication? Yes or no? That means write like this. This value is equivalent to finding this one. Do you agree or not? Yes or no? Yes. Okay. But here we have only one matrix, right? We don't have two matrices to multiply. So what we can do is we can use the same matrix, right? Because these values are present in this matrix only, right? So if I multiply this matrix twice, what should I get? The same thing we can do it for this one also. As you can see, P of 1, 0, just we can verify. This is what we are getting. So ultimately, this is nothing but 1, 0. This is this row and this row. So 1 and 0. Okay. So now we can observe a pattern here. So we can see for this particular case, it was this row and this column. If you multiply these two, you will be getting this particular value. For this particular value, this column and this row and this column. So what we have here, if you multiply these, if you get a square, and if you carefully observe now, just focus on this particular value. Can I say it's the same value that we were getting after computing it? When I was talking about this P of 0 to in exactly 2 steps. Is clear or not? Again, lag is for some time. Is it fine? Just confirm once. Okay. So I hope this point is clear, that we can observe this pattern here. And if you multiply A into A, if you perform this multiplication of A with A itself, we're getting this particular matrix. And this is nothing. So we were finding this value, right? We computed this value. And this is the value that we computed, right? 0.22. Yes or no? That means from state 0 to state 2, if I is the probability I will reach after exactly 2 steps, 0.22. So can I say that this is what we can observe here? The probability of going from I to j in exactly 2 steps is nothing but a square ij. Yes or no? Is this clear so far? Any doubt? Okay. So can I generalize this? Can I generalize this now? Yes, I can generalize. So the first problem statement that we have, which one? This one. So can I say, after understanding the concept, I can say after observing the pattern, I can say P of ij of n is nothing but A of n ij. Yes or no? Okay. So this is actually, we have understood this problem, this algorithm, but so basically this is n steps transition matrix. For higher order, we can find the probability by computing this thing like this. But actually what it is using, this is using an algorithm that is called as, the name is Chapman. Yes, the name is Chapman Kolmogorov equations. So basically, these are the equations that we are using unintentionally. We were using it, but this is what it was already proposed here. So let's understand it carefully, what it says. Just let's go through this one. We have already defined the one-step transition probabilities Pij. We know we now define the n-step transition probabilities. That means the higher order transition matrix. When I say higher order, that means power of n. So when I have to define this one, that is Pi of j of n to be the probability that a process in state I will be in state j after n additional transitions, that will be given by this, which is P of ijn is equal to probability of, yes, so xn plus m, that means the total number of steps, you can say, n additional transitions. So in this example, they have considered that few steps you have already taken, that means m steps you have already taken. Now you are taking n additional, so that is the reason why n plus m. So x of n plus m is equal to j. What is the probability that the previous state, or you can say previous state, current state, that is xm is equal to I. That means from current state you have to go to the next state. So this is what we want to find out, and this is given by this thing only, right? So this is the same thing that we have followed. Probability of ik n. So it's like something. Let me explain it to you. So it's like this. Probability of ij, let's say n. It is same as writing of probability of a. Let's say you take r steps, and then probability of k j remaining steps. So it's like this. Is it clear? Okay. The same thing is mentioned over here as well. And this is the derivation. Again, the derivation is not very important, but you can just go through it. You will understand it. Again, it is not important for your exam point of view. So this is Chapman Kolmogorov equations. And they have also mentioned like this, that if we let P of n denote the matrix of n step transition probabilities, this one, right? P of ij of n that we were calculating, right? From I state to j state after exactly n steps. So we can write it like this. This matrix can be written as P of n plus m, that means the total steps will be equal to P of n into P of n. For example, this dot is nothing but the matrix multiplication. And if you carefully observe, this is what we have seen, right? So P into P, that means P square, and this is the thing. That means P after two steps is nothing but P square ij. Yes or no? The same thing we have seen. So this is what it is talking about. And by induction also we can write P of n is equal to P of n minus 1 into P. P of n minus 1 into P, that means the steps so far, and then whatever remaining steps you have to reach the final state. So this is what you have, and this is nothing but P of n. That means the higher order transition matrix, n step transition matrix. It is equal to that. So that is the n transition, maybe 10 times. Is all clear? No. Okay, take your time. Just look at all the equations. If you have any doubt, you can ask. रील जैसी चल रहा है या मेरे में बफर हो रहा है? Any lag is there? Again, just confirm once. रुक क्या आ रहा है? I don't know what is the issue. Like from my end, the internet speed is fine, but let's test it out. Let me check the speed. It is more than 100 Mbps only. I don't know why it is happening, but Yeah, that you have to just keep it in mind. Derivation is not that important, but I talked about the entire step so that you can understand why we are getting this, because there is no point in just mugging up the concept, right? You should be able to understand, and once you understand, you should be able to make other understand also, because if you are able to understand the other student or maybe your batchmate or someone else, that means you have understood it clearly. Are you getting this point? This is what we have seen in this Chapman-Kolmogorov theorem, you can say. Okay, this is the calculation that we have written. See this this, and then we can end this class. Upload speed is low from my side. Download speed is 147 Mbps. Okay, don't worry of like वीडियो ऑफ हो रहा है, वीडियो देख के क्या करोगे यार? Just if you are getting my voice clearly, if you are able to understand what I'm saying, that is more important, right? Is there any problem in the audio? And okay, I should make my video in that case it will ask for refresh, and I don't want actually. Am I audible now? Am I audible and visible now? Okay. I think I just switched off my camera from this browser and it wanted me to reload the website. So now I hope it is fine. So let's continue. Okay, without wasting any time. Okay, so in order to solve this particular question, let's read this first. Example 41, what it says. We are forecasting the weather. Suppose that the chance of rain tomorrow depends on previous weather conditions only. So again, it is clearly saying that you have to assume this Markov property, right? Only through weather or not it is raining today, not on the past weather conditions. So you are just your prediction, your future prediction will only depend on whether it is raining today or not on the previous past weather conditions. Suppose also if it rains today, now it is raining today, then it will rain tomorrow with the probability A. It is given to you. And if it does not rain today, this is not A, this is alpha. And if it does not rain today, then it will rain tomorrow with probability B, beta. So what is given to you is, you can say that probability of rain tomorrow, given that it is raining today itself, it is raining today also. This is given to you. Probability it will be given that not. Is this clear? This is what given to you, right? Okay. Now, if we say that the process is in state 0 when it rains and the state 1 when it does not rain. So there are two states. One state is it is raining and it is not raining. Then the above is a two-state Markov chain whose transition probabilities are given by this. So if this is alpha, we know that this is going to be 1 minus alpha because the row sum will be equal to 1. And if this is beta, this will be 1 minus beta. Is this clear so far? This example is clear or not? Just tell me this first. Example 4.1. If it is clear, then we can proceed to this particular, solving this particular question. Clear? Any doubt? Just let me know. Okay, fine. So let's read the question now. Consider example 4.1. We have considered it. Okay, in which the weather is considered as two-state Markov chain. Now, if alpha is equal to 0.7 and beta is equal to 0.4, then calculate the probability that it will rain 4 days from today, given that it is raining today. Draw chain. Okay, let's draw chain. So let's say one state is state 0, or let me just write like this: state 0 and state 1. So writing state 0 means what? Okay, and state 1 is saying what? Does not rain today, or not raining today. Clear? These are the two states that we have. Fine. Now this alpha is what? Alpha is simply rain tomorrow with probability. If tomorrow also, carefully see this. If it rains today, if it tomorrow also, that probability is 0.7. If it rains today and it will not rain tomorrow, carefully. If it does not rain today and it will rain tomorrow. If it does not rain today and it will rain tomorrow, that probability is what? 0.4. Is this clear so far? So if this is given to you, can I say now you can find the remaining also? That means if it rains today, it will not rain tomorrow. You can find like this. Yes or no? That will be what? 0.3. And what about this? If it does not rain today, it will not rain tomorrow. That means 0.6. Now, do you have any doubt in this Markov chain model? Not model, Markov chain. Any doubt, anyone? Manjunath, is it clear? Okay. But both states are today only, right? Both states are today, but just consider it as a future prediction, right? You are trying to predict it future, right? So if you are present at one state, you cannot say you can future states, right? Like if I ask you what is the probability that it is rain, and what probability that after 2 days it will be raining, then are you going to make all those states? Or after 4 days, are you going to make those number of states? So this is a state transition diagram. This is a Markov chain. Here, understand it this way. Present day is raining today. That means you are standing over here. Clear? Now, will it rain tomorrow? When you are going to go to this, will it rain tomorrow? That means yes, tomorrow again. And let's consider as a time. Just tomorrow it will again rain. So you go back to the same state. Are you getting it or not? So these transitions are nothing but the probabilities from one state to the next state, from current state to the next state. Are you getting it now? Is this clear to all of you? How the transitions are happening? Okay. So whenever you are confused, just stand at a particular state and you want to go. It is raining today, so you are standing here. Now you want to check whether it will rain tomorrow or not. So that means representing what? It is raining, or it is this clear? I hope it is clear now. Fine. And similarly here also, if it is, let's say if it is not raining today, so you are standing over here, you are standing over here. Now I want to check whether it will rain tomorrow. So I will go to that state which indicates that it will rain. So from not raining to raining, I'm making a transition. I hope now it is clear, crystal clear. Exactly. States, consider states as the current state. Transitions are from one state to another state, or from current state to the next state. As simple as that. Okay. So now the question is, calculate probability that it will rain 4 days from today. That it is raining today. It is given to you, it is raining today. Now, after 4 days, that means after 4 days, still it will be raining. You have to find the probability. So can we use the same concept that we have on probability matrix? Yes, we can fill the values and want to check after 4 days. So can we multiply? Can we do the matrix multiplication of the same matrix 4 times? Yes or no? So if I do that, this is my P. If I do that, so P4 basically we have to calculate. So first you will be calculating P square, which is nothing but this thing, P of ij after 2 days. Then you calculate this basically, which is nothing but P of ij. So ultimately, yes, exactly. And that is your after 2 days, whether it will rain today, whether it will rain tomorrow. If it is raining today, whether it will rain after 2 days or not, right? So just you need to perform this matrix multiplication and you need to find that desired probability. I hope it is crystal clear to all of you how we are using that n steps transition matrix concept, which involves Markov chain, which involves Chapman-Kolmogorov equations to solve this particular question. Is it crystal clear to all of you? Do you have any doubt, anyone?